stage to talk about.
Yep. Okay. So let's talk about QUIC, which is a new network protocol, and the name stands for QUIC UDP Internet Connections, which I think sounds incredibly boring. So I thought, how about instead, just for the day, we say that QUIC instead means Aquaman, Bruce Wayne, and the fastest man alive combined. Allow me to elaborate. You see, before we can understand QUIC, we need to understand the problems that it's trying to solve. And when we talk about networks, it's usually in this form of kind of a layered stack, where at least on the web we have HTTP on top. Then we have transport layer security, and then we have transport control protocol, TCP. Now, I like to think that HTTP is kind of like Aquaman, because he understands the fish language. And HTTP is a thing that tells us which kind of messages we can send on the web. And who better to be in charge of security than the best detective in the world? And for transport, we mainly want someone fast, someone who can get the job done. And that's, of course, perfect for Superman. Now, the reason for this layered stack is mainly flexibility. It doesn't really matter if we have Wi-Fi or 4G at the bottom layers. Everything else can stay pretty much the same. Now, to keep that flexibility, these layers, of course, have to be very loosely coupled. They can't really communicate too much, or we would lose the ability to swap them out. This, in turn, leads to some inefficiencies, because some of these protocols are going to want to do very similar things, don't know that about each other, and so we end up doing some things twice. I'm going to give you an example. We all know that Aquaman loves to write, and he has a pen pal. It's a white whale called Richard. And when Aquaman has written a letter, he goes to Superman and he says, I think Richard is at about these coordinates. Would you kindly take this letter to him? And of course, Superman is going to say, no, because he wants to first go out there and check that Richard is actually at those coordinates, which takes him about 1 round trip. And when he gets back, Batman is waiting for him. And he says, how can we be sure that that's actually Richard? How do we know that it's not a supervillain dressed like a whale? So he forces Superman to go back and get Richard's credentials. And when they check out, he has to go back again because Batman wants to have a super secret password to encrypt all the messages. So we see that finally it takes us about 4 round trips until we can finally get a response from our initial letter. And Superman is quite fast, but at transcontinental distances, even he will take about half a second for this, which is, of course, quite slow. The good thing is, once this connection has been set up, we can start talking about all kinds of things. About his love affair with Wanda, about next week's poker game, about what they're going to wear to SpongeBob's birthday party. And just like a nice, busy WhatsApp group, they're going to be talking about all these things at the same time, interchangeably. They're going to jump from one topic to the next and back again. And the problem now comes that Superman is a bit clumsy. He sometimes drops things. So if you imagine, please, Superman flying around with a whole bunch of pages in his arms, and he ends up at this location, and he notices that one of the yellow pages has gone missing. You all know if you have a long letter, 1 page is missing, there's a high chance that the rest won't make much sense anymore. So the only thing that Superman can do is hold back these other yellow pages while he goes back and fetches a new copy of the one he lost. Before he leaves, of course, he's going to give all these other pages to Aquaman, who can start reading them, because these are all independent topics, so you don't need to have read one to understand the others. This is kind of the best that we can get, the best that we can do when we have some packet loss. In practice, however, it's not that easy, because what Superman sees actually looks a lot more like this. He doesn't know about the colors, he doesn't know about the different resources. That is because he and Aquaman do not communicate because they're on the different layers. He doesn't understand the fish language, and this thing is encrypted anyway. So for TCP, this is all just one giant bit stream. It looks like one big resource. This means if one of these packets get lost, TCP has no other choice than to block everything that comes behind it, not just those 2 yellow pages that were actually impacted. And this is what we call the TCP Headofline Blocking problem. Luckily, for a very long time, this was mainly a theoretical problem. It didn't really happen all that much in practice. And the reason for that is that Aquaman is a bit stupid. He can be a bit dense. I told you before that they're talking about all these things at the same time. I kind of lied. He wouldn't be able to mentally deal with that. So HTTP 1, you can actually send multiple requests at the same time. That's not a problem. But the responses have to be delivered totally and in order of request. This means if this first resource is slow, for example, it's very large, or it has to wait for some database access to be generated, it has the potential to block everything that comes behind it, even though there might have been some time on the network to send other things. That's simply because HTTP 1 cannot deal with out-of-order responses. And we call this, very originally, the HTTP Headofline Blocking problem. Right, so the HTTP Headofline Blocking problem. Now, Aquaman is a bit dense, but he understands that this is an issue. And by now, we all know what happens if you give a powerful orange man a difficult problem. He's going to use his brawn rather than his brain. And Aquaman is quite powerful. He is a half-god. So what he thinks is the ideal solution here is to open magical portals into parallel universes. Parallel universes that each have their own copy of Batman and Superman that he can use. And this suddenly enables him to do things at the same time, because now he knows, okay, portal 1, that's the pink stuff. Portal 2, that's the yellow stuff, and so on. So if you're using HTTP 1, your browser is going to open up to 17 of these parallel connections to download things at the same time. It does this to kind of circumvent these head-of-line blocking problems. It doesn't really solve them, it just makes them happen a lot less. Because, for example, if we now have packet loss on one of these connections, it won't impact the others. They can just keep working as usual because they're completely independent Superman working behind the scenes. This works really, really well, but has its own overhead because we have to set up and maintain all of these connections. Not to mention what we're doing to the fabric of space-time. So let's summarize. We have 3 main problems. Our connection setup is quite slow. If we have packet loss, things can be blocked, even though they have already arrived at the client. And if we have a slow first resource on HTTP, that can also block things behind it. The solution for these last 2 works, but has a lot of overhead by itself. So let's try to solve these things one by one and start at the top with Batman. This is what I showed you before, and that's kind of the situation in TLS 1.2, which is the current version of the protocol that's most widely deployed. We see that to optimize this, the simplest thing to do is to ask Batman to do his 2 things in one round trip. And that was actually kind of possible in some situations for TLS 1.2, and it's now the default for TLS 1.3, which is the new version of the protocol, very recently finalized and is now being implemented. If we want to optimize this even further, though, we need to start finally having some communication between these layers going on. For example, we can have Batman and Superman working together using a technology called TCP Fast Open, which allows us to send some extra data in the initial TCP SYN packet. So this is great. We've already had twice the performance that we had before. But what we really want, a holy grail, is of course to do everything in a single round trip. There's a bit of a problem with this, though, because Batman insists that everything has to be encrypted, including this first HTTP request. Now, we can only encrypt things if we have an encryption key, and we have to get that from the server. That's kind of a problem here. So what's going to happen in practice, the first time you connect to a server, that's going to be the 3rd column, it's going to give you 2 encryption keys, one for use now and one for use in the future. So that when you reconnect to a server that you already know, and that also remembers you, then you can use that second encryption key to also encrypt that first request. This encryption isn't going to be as good as the encryption after that, but it's more than secure enough to allow a wide range of interesting use cases. Online you will see this marketed as 0 RTT, which basically means that there is 0 overhead, while before we had 3 RTTs of overhead for setting up this connection. So we see that this is great, and that most of this improvement comes from moving from one version of the protocol to the next. We've gone from Adam West to Christian Bale, and as always, we ignore Ben Affleck. Now we all know that there's another protocol that has gone through a similar change quite recently, because HTTP has also gotten better, smarter, and sexier. The nice thing about HTTP 2 is that the main thing that it does is solve that head-of-line blocking problem on this layer. Remember, what we really want for HTTP is to be able to talk about multiple things at the same time. That wasn't possible in HTTP 1 because it sends basically all resources as one big letter without any type of indication to which resource these individual pages belong. So the main innovation in HTTP 2 is incredibly simple. It says, how about instead of writing letters, we're just going to start using index cards. Each paragraph we want to send, we write on a separate index card. On the top of each index card, we put to which resource this data belongs. Now, whenever Aquaman receives an index card, he just has to look at the header and he says, okay, this is the pink stack. This is the yellow stack. This quite simple system now allows us to what they say is multiplexing of multiple resources on that same connection. This is great, because now we don't need those 17 parallel connections anymore to be able to download things at the same time. So HTTP 2 kind of solves 2 problems at once, the HTTP Headofline Blocking and the overhead of the mitigation that we did before. So no wonder that this has been marketed so aggressively. The problem, though, with this is that now we fall back to a single Superman. We no longer have 17, we only have 1. And if you remember, Superman had his own problems in the TCP Headofline Blocking if there is packet loss. And so I have seen and done experiments that have shown that HTTP 2 can be up to 5 times slower than HTTP 1 on networks with packet loss. So that is a huge impact, and it makes it very, very important that we finally solve this TCP Headofline Blocking problem. And by now, I think you all think you know where I'm going, right? We're just going to introduce a new version. This is kind of where my carefully crafted superhero analogy falls down. Because when this has happened on the big screen, it's kind of failed to materialize on the internet. There is no such thing as a TCP 2.0. That's not because we haven't tried. We've been trying for decades. The problem is that TCP is too popular. It's too widespread. We all know that the internet is kind of an interconnected series of devices, and they all have their own implementation of TCP running. Now, most of the developers of these implementations apparently can code about as well as me, which means these things are riddled with bugs and break easily. This means if we want to change anything about TCP, there's a very high chance that we will break at least some of these what we call middle box implementations. So if we want to change anything, we have to wait until all of these implementations have added support for it before we can deploy it at scale. I talked before about TCP Fast Open. That has been in the Linux kernel since 2012, and even today is only very sparingly used because a lot of implementations are still lacking support for it. So if we want to solve the TCP Headofline Blocking problem, we kind of have 2 options. We can either wait a full decade for everyone to catch up, or we can make a bold choice, a kind of controversial choice. We can acknowledge that TCP simply isn't evolvable anymore and decide to replace it with something else. Exit Superman. Enter the Flash, aka UDP. If you don't know what UDP is, it's kind of a bare bones version of TCP. The Flash doesn't fly, he doesn't shoot laser beams from his eyes, he has no super strength, he's just really, really fast. UDP doesn't care about packet loss. If one of the packets is lost, it just ignores them. Normally that's not what you want because it means you have to deal with that in the application layer. But here is of course exactly the kind of flexibility that we need. And finally, we're about ready to talk about what QUIC now really is. On the left, we have the top of the line TCP stack, the best you can get today. And we see that QUIC kind of spans all the 3 layers. It is a massive block of layer violations as it integrates all these 3 things together. And in reality, it kind of looks even more like this. Because QUIC is still going to use TLS 1.3. It still has all that 0 round-trip time goodness. It then builds on top of UDP, re-implementing a lot of what we know and love from TCP. And it still uses the HTTP2 semantics, just not the exact implementations. Because what QUIC is going to do is it's kind of going to steal that multiplexing idea from HTTP2. It's going to steal that index card and bring it down one of the layers. And then it's going to build on top of UDP custom packet loss recovery logic. And the core thing that this enables, the main reason for QUIC, is that these 2 can now finally communicate. Aquaman can finally talk to the Flash directly. The Flash finally understands that we have multiple resources at the application layer, and if one of them is experiencing packet loss, all the rest does not have to be blocked. Solving, of course, the TCP Headofline Blocking problem. But you see, for this, we had to do a lot of work. We have to invent a completely new protocol over 3 different layers, re-implement a lot of things. And we also see that most of what I've talked about today, HTTP2 and TLS 1.3, work perfectly well on TCP as well. So is it really worth all that effort to do all that work to solve that one TCP Headofline Blocking problem? And not really. The answer is no. So the people who made QUIC said, if we are going to do this effort anyway, we are going to do it right. We are going to solve all the other problems as well. So QUIC is kind of like a combination of everything that we've learned about networks over the past 3 decades. All the best practices in one neat little package. Next to performance, QUIC also focuses very heavily on security. Most of these older protocols have been abused in the past by hackers for things like distributed denial of service attacks. So what QUIC does by design is integrate mitigations for almost all of the known attacks into its implementation to make it much, much more difficult to abuse. And of course, for those future security holes that we might find, QUIC wants to stay very flexible to be able to change where needed. We saw before that this was a real issue with TCP because these middle boxes were looking at traffic and making the wrong assumptions. And that is mainly because we are mainly encrypting the data on the HTTP layer, but not on the bottom layers. All the TCP stuff is out in the open on the wire for anyone to read. So the solution that QUIC does for this is to say we're going to encrypt almost everything, including our own metadata. Things like packet numbers, packet types that are normally visible with TCP are now also encrypted in QUIC, which is, of course, great. The idea is that the less these middle boxes get to see, the less they can break. That's, of course, great for QUIC and its users, and terrible for people who make middle boxes. So it's a very, very political issue, and a couple of weeks ago, there has been a 2-hour discussion about whether or not to add a single bit to be visible to the middle boxes. 2 hours for 1 bit. I'd say look it up on YouTube, it's quite entertaining. Another nice thing I think about QUIC is that it tries to account for how people are actually using the internet in a modern setting. For example, you're all here now on Wi-Fi, but if you were to go outside, you would switch to 4G. Any open TCP connections you might have will automatically close down and have to reconnect because you now have a new IP address. So what QUIC does is instead assign you a unique connection ID that will remain the same no matter how many times you change your IP address. And it takes this one step further. It says, oh, you have Wi-Fi and 4G. Why not use them both at the same time? 2 networks, extra bandwidth. And that's the idea behind multipath. And that has been shown in a lot of research to be very, very interesting for performance improvements. QUIC does a lot of other stuff next to this as well that I don't really have time to go into today. But my personal favorite is probably this: custom congestion control. If you don't know what that is, it's mainly the mechanism that prevents you from sending too much data. It prevents you from overloading the network. Normally, again, this is something that TCP does for us. But that's not always optimal. TCP usually has a single general purpose algorithm that it uses for all connection types. That works well most of the time, but it can be very detrimental in some specific edge cases. So what QUIC allows is to say, we can have the optimal congestion algorithm for each independent connection type. If you combine this with something like the Netinfo API, which allows you to query the browser and see what type of connection you're currently on and how much bandwidth you have to use, then you can start to tweak this and have the perfect micro-optimization for each individual user at that exact moment and for the exact page you're trying to serve them, which in turn can help with making things like HTTP2 server push a bit more practically applicable. So, like I said, I think this is one of the most interesting things about QUIC, one of the things that I will be researching. If you want to know more, come talk to me afterwards, because I think that by now, most of you are craving some numbers, right? How much performance gain can we actually expect after all that work? And the simple answer is, we don't. And the reason for that is that QUIC was originally developed by Google. A couple of years ago, they very, very rapidly deployed this on their servers and in Google Chrome, and it's now serving over 7% of the total internet. So QUIC has been battle tested at scale, but really only by Google. Now, we like Google. We trust Google. If Google says something works, we say, standardize it. So that's what happened last year when we got the new IETF version of QUIC. This version is very, very similar to the Google version in concept, but it changes a lot in terms of some implementation details. Now, when I submitted this talk last year, I thought we would have been much, much further along by now. I hoped that I would have some data from our own implementation to be able to share with you, but boy, was I naive. There are currently over 14 implementations that we know of, and none of them is even remotely ready for any type of performance testing, let alone browser integration. And that's expected to stay that way for a couple of months still. Now, I don't want to let you go home without anything, so I suggest that instead I give you some data on the left version that should be relatively transferable to the standardized version because they're still quite similar in the bottom line. Most of that data comes from academic research papers, and the first one is from Google itself. And they tested QUIC on the Google Search app. And they found about 3.6 to 8% improvement. When I first saw that, I was kind of disappointed. I was like, 8% for all that work? Until I realized, this is Google Search. This is quite possibly the most optimized application in the world. These guys throw parties if they have a single % consistent improvement, probably. And this is on average. At the 99th percentile, they measure up to 16% improvement, which is something that I'll sign for any day. Now, they noticed that most of this comes from that 0 round-trip time connection setup. And that also explains the worst numbers on mobile here. Because remember, the 0 round-trip time, you can only do that to a server that you have already seen before. Now, on mobile, you're much more likely to be moving around, and Google's load balancers might send you to different data centers that you haven't seen before. So that's something that should be improvable in the future, and you shouldn't have to deal with that much if you're not operating at Google scale. So we see that Batman is doing his job quite well, mission accomplished. But how about the Flash? How about the reason that we moved to QUIC in the first place is to be better for lossy networks? Again, Google has tested QUIC on YouTube and has found about a 20% less rebuffering for video content on networks in India, which are generally considered not to be of the best quality. There's another paper that says we get about a 14% of actual page load time improvements in the actual browser, which is nice. And then there's another paper that tested QUIC on packets with and without, on networks with and without packet loss. And of course, QUIC is going to be a bit slower with packet loss, but only about 20%. While HTTP2 is slower by over 200% in those cases. Now this sounds great, but this wouldn't be academia if there weren't also papers that claim the exact opposite results. So there's one paper that says that QUIC is terrible for video streaming. It consistently selects the lower quality. There's one paper that says that if you have an inconsistent latency, that will cause packets to be reordered, and the current implementations of QUIC really can't handle with that. And there's one of the older papers that says that you can have 30% slower page load times if you have a network that has packet loss, but also a very high bandwidth. Now, I'm not really here to tell you which one of these two to believe. My interpretation is more like QUIC has a huge amount of potential, but the implementations still need a lot of work until we can see consistent improvements over all of these use cases. And that's another thing that shows from this quote from Google, where they find that QUIC takes about twice the amount of CPU on the server than TCP does. This again is because TCP is so old, it has been implemented into the operating system kernel and sometimes even hardware. While QUIC is so new, it's still living in what they call user space, which is a lot slower. There's another paper that looked at that in the mobile device scenario, and they found that in the cases that QUIC performs suboptimally, most of the time it's because the network is waiting for the mobile CPU instead of the other way around, which is completely bonkers. Now, it has to be said that this user space implementation is exactly one of the things that allows us to evolve QUIC so rapidly. If we have a new version, we just have to have a new server and a new browser version. That's it. We don't need to update our OS or any of the middle boxes. So this is a very interesting trade-off that we can make. And of course, this is expected to get better over time, but there will always be kind of a performance cost to QUIC, even at the long run. With that, I'm kind of ready to summarize. The main point about QUIC is that it moves away from TCP into UDP. This allows us the option to pull in everything but the kitchen sink, to focus on both security and performance and flexibility towards the future, all at the same time. For us, it promises performance improvements on almost all use cases, but especially on slow networks with a lot of packet loss, aka emerging markets. Now, what does this mean for all of us here today? Not that much. We don't really have anything to deploy. But if you're not currently on HTTP2, it might be time to start thinking about switching. Unless, of course, all your users are at those emerging markets, then maybe just switch to HTTP1S. But look at your own data to make that decision, of course. When QUIC then does arrive, I think about late next year or maybe 2020, it'll probably be as simple as changing a variable in your server config, just the way it was with HTTP2 as well. But the major difference with HTTP2 is going to be that with QUIC, we're going to get a lot more parameters to tweak, a lot more knobs to turn to be able to micro-optimize our performance for individual users. And like I said, that is a part that I am absolutely most excited about. Now that's all of it from me. And as a conclusion, I just want to make you all a promise. A promise that if I ever get to do a follow-up to this talk, I will do my very best to expand the cast to also include the incredible Wonder Woman. Thank you.